Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 3, Projectivities of the Primitive Geometric Forms of 1, 2, and 3 Dimensions. Section 28, Projective Transformations of Two-Dimensional Forms. Definition: a projective transformation between the elements of two two-dimensional or two three-dimensional forms is any one-to-one reciprocal correspondence between the elements of the two forms, such that to every one-dimensional form of one there corresponds a projective one-dimensional form of the other. Definition: a collineation is any one-to-one correspondence between two two-dimensional or two three-dimensional forms in which to every element of one of the forms corresponds an element of the same kind in the other form, and in which to every one-dimensional form of one corresponds a one-dimensional form of the other. A projective collineation is one in which this correspondence is projective. Unless otherwise specified, the term collineation will, in the future, always denote a projective collineation. Footnote: how far a collineation must be projective will appear later. In the present chapter, we shall confine ourselves to the discussion of some of the fundamental properties of collineations. In this section, we discuss the collineations between two-dimensional forms and shall take the plane, planar field, as typical. The corresponding theorems for the other two-dimensional forms will then follow from duality. The simplest correspondence between the elements of two distinct planes, pi prime, is a perspective correspondence, whereby any two homologous elements are on the same element of a bundle whose center O is on neither of the planes pi or pi prime. The simplest collineation in a plane, i.e., which transforms every element of a plane into an element of the same plane, is the following. Definition: a perspective collineation in a plane is a projective collineation, leaving invariant every point on a given line O and every line on a given point O. The line O and the point O are called the axis and center, respectively, of the perspective collineation. If the center and the axis are not united, the collineation is called a planar homology. If they are united, a planar elation. A perspective collineation in a plane pi may be constructed as follows: that any line O and any point O of pi be chosen as axis and center, respectively, and let pi sub 1 be any plane through the line O distinct from pi. Let O1 and O2 be any 2 points collinear with O, and in neither of the planes pi or pi sub 1. The perspective collineation is then obtained by the two perspectivities. The pencil P is perspective with center O1 to the pencil P1, which is perspective with center O2 to the pencil P prime, where P is any point of pi and P1 and P prime are points of pi 1 and pi, respectively. Every point of the line O and every line through the point O clearly remain fixed by the transformation, so that the conditions of the definition are satisfied if only the transformation is projective. But it is readily seen that every pencil of points is transformed by this process into a perspective pencil of points, the center of perspectivity being the point O, and every pencil of lines is transformed into a perspective pencil, the axis of perspectivity being O. The above discussion applies whether or not the point O is on the line O. Theorem 9. A perspective collineation in a plane is uniquely defined if the center, axis, and any two homologous points, not on the axis or center, are given, with the single restriction that the homologous points must be collinear with O. Assumptions A and E. Proof: let O and O be the center and axis respectively. Figure 29. It is clear from the definition that any two homologous points must be collinear with O, since every line through O is invariant. Similarly, dually, any two homologous lines must be concurrent with O. Let A and A prime be the given pair of homologous points collinear with O. The point B prime homologous to any point B of the plane is then determined. we may assume B to be distinct from O and A and not to be on O. B' is on the line OB, and if the line AB meets O in C, then, since C is invariant by definition, the line AB equal to AC is transformed into A'C. B' is then determined as the intersection of the lines OB and A'C. This applies unless B is on the line AA'. In this case, we determine as above a pair of homologous points not on AA', and then use the 2 points thus determined to construct B'. This shows that there can be no more than one perspective collineation in the plane with the given elements. To show that there is one, we may proceed as follows. Let pi sub 1 be any plane through O distinct from pi, the plane of perspectivity, and let O1 be any point on neither of the planes pi or pi sub 1. If the line AO1 meets pi sub 1 in A1, the line A'A1 meets OO1 in a point O2. The perspective collineation determined by the two centers of perspectivity O1, O2, and the plane pi sub 1 then has O and O as center and axis respectively, and A' as a pair of homologous points. Corollary 1. A perspective collineation in a plane transforms every one-dimensional form into a perspective one-dimensional form. Assumptions A and E. Corollary 2. A perspective collineation with center O and axis O transforms any triangle none of whose vertices or sides are on O or O into a perspective triangle, the center of perspectivity of the triangles being the center of the collineation and the axis of perspectivity being the axis of the collineation. Assumptions A and E. Corollary 3. The only planar collineations, whether required to be projective or not, which leave invariant the points of a line O and the lines through a point O, are homologies if O is not on O, and elations if O is on O. Assumptions A and E. Proof. This will be evident on observing that in the first paragraph of the proof of the theorem, no use is made of the hypothesis that the collineation is projective. Corollary 4. If H is a perspective collineation, such that H of O is equal to O, and H of O is equal to O, H of A is equal to A prime, H of B equal to B prime, where A prime, B prime are collinear with a point K of O, then we have Q of OAB, K B prime A prime, by assumptions A and E. Proof. If C is any point not on AA prime and H of C is equal to C prime, the lines AC meet A prime C prime in a point L of O, and BC and B prime C prime meet in a point M of O, and the required quadrangle is C prime L M, chiefly figure 32 on page 77. Theorem 10. Any complete quadrangle of a plane can be transformed into any complete quadrangle of the same or a different plane by a projective collineation, which, if the quadrangles are in the same plane, is the resultant of a finite number of perspective collineations. Assumptions A and E. Prove. Let the quadrangles be in the same plane, and let their vertices be A, B, C, D, and A prime, B prime, C prime, D prime, respectively. We show first that there exists a collineation leaving any three vertices, say A prime, B prime, C prime, of the quadrangle A prime, B prime, C prime, D prime invariant and transforming into the fourth, D prime, any other point, D3, not on a side of the triangle A prime, B prime, C prime. Figure 30. Let D bar be the intersection of A prime D3 and B prime D prime, and consider the homology with center A prime and axis B prime C prime, transforming D3 into D bar. Next, consider the homology with center B prime and axis C prime A prime, transforming D bar into D prime. Both these homologies exist by Theorem 9. The resultant of these two homologies is a collineation leaving fixed A prime B prime C prime and transforming D3 into D prime. It should be noticed that one or both of the homologies may be the identity. Let O1 be any point on the line containing A and A prime, and let O1 be any line not passing through A or A prime. By Theorem 9, there exists a perspective collineation pi sub 1 transforming A to A prime and having O1 and O1 as center and axis. Let B1, C1, D1 be points such that pi sub 1 of A, B, C, D is equal to A prime B1, C1, D1. In like manner, let O2 be any line through A prime not containing B1 or B prime, and let O2 be any point on the line B1, B prime. Let pi sub 2 be the perspective collineation with axis O2 and center O2 and transforming B1 to B prime. Let C2 equal to pi sub 2 of C1 and D2 equal to pi sub 2 of D1. Here, pi sub 2 of A prime B1 C1 D1 is equal to A prime B prime C2 D2. Now let O3 be any point on the line C2 C prime, and let pi sub 3 be the perspective collineation which has A prime B prime equal to O3 for axis, O3 for center, and transforms C2 into C prime. The existence of pi sub 3 follows from Theorem 9 as soon as we observe that C prime is not on the line A prime B prime by hypothesis, and C2 is not on A prime B prime, because if so, C1 would be on A prime B1, and therefore C would be on AB. Let pi sub 3 of D2 be equal to D3. It follows that pi sub 3 of A prime B prime C2 D2 is equal to A prime B prime C prime D3. The point D3 cannot be on a side of the triangle A prime B prime C prime, because then D2 would be on a side of A prime B prime C2, and hence D1 on a side of A prime B1 C1, and finally D on a side of A B C. Hence, by the first paragraph of this proof, there exists a projectivity pi sub 4 such that pi sub 4 of A prime B prime C prime D3 is equal to A prime B prime C prime D prime. The resultant pi sub 4, pi sub 3, pi sub 2, pi sub 1 of these four collineations clearly transforms A, B, C, D into A prime B prime C prime D prime respectively. If the quadrangles are in different planes, we need only add a perspective transformation between the two planes. Corollary, there exist projective collineations in a plane which will effect any one of the possible 24 permutations of the vertices of a complete quadrangle in the plane. Assumptions A and E.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.